Welcome to DCL 302, generating single sideband. First thing we got to talk about is AM sidebands, because single sideband is actually AM radio without one of the sidebands and without the carrier. So in order to really understand SSB, or single sideband, we've got to take a little deeper look at AM sidebands. So here's our basic transmitter, 3 megahertz carrier oscillator. For right now, we're just going to modulate it with a 2,500 hertz tone. So the two are combined in the power amplifier. There's a 100 watt RF signal and 50 watts of audio if we speak real loud and turn the gain all the way up. With this setup, what will happen is when we key the radio, we get a 100 watt signal. As the sine wave coming from here goes through its cycle, when it peaks, the modulator throws all of its energy into the power amplifier. The power amplifier throttles up to 400 peak watts. When the sine wave goes negative, the power amplifier drops to essentially 0 watts. So what we're thinking of here is the audio signal is adjusting the amplitude of the amplifier in synchronization with the phase of the audio signal. So we talk about AM radio as being amplitude modulated, as in the amplitude of the RF carrier wave varies in relation to the audio that is modulating it. Now that's one way to look at it. We're adjusting the power of the amplifier. But there's something else going on. It's kind of a unique thing. The power amplifier and modulator are working together as sort of a mixer. We have a 3 megahertz signal coming in, combined with a 2.5 kilohertz signal. So we have 3 megahertz carrier, plus we have the mix of the carrier plus the audio and the carrier minus the audio. What this really means is we literally have 3 signals. As long as there's audio, you have 3 signals. If you key the transmitter with no audio, you only have the carrier wave. As soon as you add audio, you get these outer 2 signals. They are literally thought of, and can be thought of because they are, separate signals. That means if we can generate them independently, perhaps we could only send one sideband at a time without the other sideband and without the carrier, which of course we can do. We call that single sideband. But how do we do that? Here we've got to stop for a moment. With today's technology, we can synthesize single sideband or anything else with software-defined radios. But if I explain how that works, you really won't quite get a full understanding of what AM and single sideband is. So in this video, we're going to go with the old technology. And of course, there's thousands of old style transmitters out there. We're going to talk about how this was generated before software-defined radios came along. Once you understand how it was done, the software-defined radio is easier to understand, and you will truly understand AM and sidebands. Let's talk about a circuit from electronics called the mixer, specifically the single-ended mixer. This is a unique little device that has some unusual properties. If a mixer has only one input, there's no output. But look what happens when there's 2 inputs. Now we have our local oscillator signal, and it shows up at the output. We have our input signal, and it shows up at the output. We have the addition of the 2 of them. We also have the difference between the 2 of them. As you can tell, this is starting to look like AM sidebands. So let's treat the whole thing like AM sidebands. Let's pretend the RF amplifier and modulator are a mixer. We have our local oscillator running at 3,000 kilohertz or 3 megahertz. We have some audio. Now what we have at the output is we have our carrier that we started with. We have the carrier plus audio, carrier minus audio, and the audio, because this is a mixer. Now, these tuned circuits right here are tuned for RF frequencies. They are not going to pass audio. That's why audio is in blue. It's there, but it doesn't really count because it can't get through these circuits. So at the output, we have just these three signals, which, by the way, are the very signals you have coming out of an AM transmitter. Well, we could talk about mixers if you want to, but it would be better if we moved on, because we don't have a lot of time. Let's talk about balanced mixers instead. In fact, let's not even talk about balanced mixers. Let's jump all the way to the double balanced mixer, primarily because a double balanced mixer has great port isolation. I'll explain what that is in a minute, but you're going to see how important it is. Now, there's two things about the double balanced mixer. It requires a lot of drive, and it doesn't like reactive terminations. Well, fortunately, because of what we're doing in radio, we don't care about those two parameters. Well, we don't care about the high drive requirement. We can handle that. As far as the problem with reactive terminations, well, we have ways of dealing with that too, so that's not really a big deal. My point is, the disadvantages of the double balanced mixer are not going to slow us down one bit. Let's look at the double balanced mixer as a signal processor, the way we were using the single-ended mixer. We have our local oscillator, we have our signal, and they mix. But all we have is the sum of the two and the difference. This is what I meant by port isolation. Any signal shows up here will never show up here. Any signal showing up here will never show up here. That's how we say there's great port isolation between this port and either one of these ports. But what that really means is we have a lot less to filter at the output. We have our choice. We can take the sum or the difference. So we've automatically cleaned up the output of the mixer by going with a double balanced mixer. Let's now treat the double balanced mixer as a modulator or as a transmitter. Right away you can see the advantage. Here's my local oscillator, which we're now going to call the carrier oscillator. And I've got my audio signal coming in. And what do I get? By now you recognize I get my upper sideband and my lower sideband, no carrier. So I've taken a step toward single sideband. Yeah, I still got two sidebands. I've just eliminated the carrier. So I'm partway there. There are two basic ways from the past to generate single sideband: the phase method and the filter method. It is much easier to understand SSB with the filter method, so that's what we're going to stick with. First of all, what really is SSB? Well, we already know. It's where we transmit one AM sideband and nothing else. No carrier, no second sideband. Can we mix the carrier and the audio in such a way that we do it at a low energy level? Well, the double balanced mixer requires a high drive level, but what they call a high drive level isn't really that much power. I'll explain that in a minute. We also need a lot of isolation between the ports of our mixer. Well, double balanced mixer takes care of that, doesn't it? So all of the disadvantages of the double balanced mixer don't matter. And the one big advantage, the port isolation, we have. So things are starting to look pretty good. The point here is, if we want to generate single sideband, we need a new kind of modulator. We need a balanced modulator, which is a form of a double balanced mixer. The double balanced mixer in the form of a balanced modulator was invented about 60 years ago. It is the single most popular form of generating single sideband there is today. Well, or there was up until the recent advent of software-defined radio. But for about 55 years, the balanced modulator was king. This is a balanced modulator. It's actually one I'm building, or I did build. It's finished. I'm building a shortwave sideband transmitter. This is my balanced modulator. Looks a little crude, I know, but everything I build is usually crude. This is the schematic diagram I ended up with. All of the components necessary, or that are there, are necessary to make it really work. Microphone audio from the speech amp comes in on the blue arrow. The local oscillator, or carrier oscillator, energy comes in on the red arrow. And the two sidebands leave on the yellow arrow. And again, this is a form of double balanced mixer. And it really saves the day for us. So let's take a look at this. So we're going to have audio in, carrier in, with just the sidebands out, but no carrier coming out. First thing we want to talk about, only briefly, is if audio comes in from the left, it will never make it to the yellow arrow because, first of all, it can't get through the 4 diodes in the bridge rectifier. But even if it could, the RF transformer won't pass audio. And these two little capacitors, well, they, together with this carrier null potentiometer, are used to set this up for a perfect balance. I'll describe the balance in a minute, but it's very important that we have a perfectly balanced circuit. This one capacitor is very interesting. You can learn a lot about circuit theory just by looking at that one capacitor. That's a 0.01 microfarad capacitor. At 3 megahertz, it has a reactance of 5 ohms. So essentially, this is a dead short, the same as this. So the bridge is balanced. At audio frequencies, this little capacitor looks like 16,000 ohms. So the audio comes in and goes into the bridge. But when RF flows in, it will flow to ground here and it will flow to ground here with no problem. Now, I talked about the high drive level of the balanced mixer. Well, that's a relative term. The input impedance to this circuit right here, as the carrier oscillator sees it, is about 100 ohms. Actually, it's about 120 ohms, but let's just say it's about 100 ohms. I found out that a half a volt of RF energy works the best in this circuit. So a half a volt squared divided by 100 ohms, according to Ohm's law, is 2.5 milliwatts. Now, in the electronic world, that's a very high drive level. But to you and me, being radio people, we can generate 2.5 milliwatts easy, so we don't care about the high drive level. It means nothing to us. So let's take a look at how this circuit works. The energy from the crystal oscillator is coming in, or the carrier oscillator, and it's splitting evenly between these two arms. This has capacitive reactance, and this has capacitive reactance at 3 megahertz. We're going to adjust this one so these balance perfectly. The potentiometer is balanced. Notice the current flow. Up, through the diode, down. Here, through the diode, to ground. It's perfectly balanced. Because it's so balanced, there's no reason for any current to flow over here. If there's no current here, then there's no current over here, and there's no output. When the polarity of the carrier oscillator reverses, electron flow reverses. We come up through here, go up, and out. We also come up through here, go up, and out. Again, notice everything is in perfect balance. So there's no flow through the transformer. All right, now we have some audio to play with. At this point right here is positive, meaning this one right here. So current flows through here and out. Then, when the polarity of the audio reverses, current flows through here and through here. Now, what's important to understand is that a diode flowing current shows a lower resistance than a diode not flowing current. Of course, the diodes are already flowing current because the RF energy is flowing in this circuit. I just don't have it shown here. But when the audio comes in, the audio level is much higher than the RF level, which means the diodes conduct more because of the audio. The problem is the audio is applied out of phase between top and bottom. So what that means is that let's just say when the top is conducting the most, this resistance here looks much lower because these diodes are flowing. So that means RF coming in through here is going to split. Part of it's going to come up here and flow through here. The other part is forced to come up here, but when it gets here, it knows that this is a relatively higher resistance than over here. So a lot of the current, some current goes this way. A lot of the current goes through here to ground. Now we have an unbalanced flow. That means we have current here, which means we have current over here, which means we have an output here. By using the audio to unbalance the bridge, we've created an output. So what is the output? What's in it? Well, remember, I said this is a mixer circuit. If it's a mixer circuit, then that means I have a 3 megahertz signal and I have a 1 kilohertz signal. They're going to mix. Well, we know the 3 megahertz signal can't get through here because that part of the circuit's balanced. But when the audio is there, it's not balanced. So now I have a 3 megahertz plus 1 kilohertz signal and a 3 megahertz minus a kilohertz signal. So now I have my two sidebands. In fact, we would say I'm sending double sideband or double sideband suppressed carrier. And this is what the spectrum looks like coming out. First of all, notice there is no carrier. We've eliminated it. We now have, let's say we have all of the audio frequencies from 450 cycles to 2,550 cycles. Let's just say we've limited ourselves to those frequencies. That's a bandwidth of 2.1 kilohertz. So what that means is I have the carrier plus 450 and the carrier plus everything up to 2,550 hertz. So all of this is audio in here. All of this is human voice. But I also have the mirror image. I have the carrier minus 450 hertz all the way to carrier minus 2,550 hertz. I've now created my double sideband signal with no carrier. If I had a filter, I could pick which sideband I wanted to transmit. The filter I want, and the math is a little funny here, the filter I want must be centered at 3.15 kilohertz, right here in the middle. Because that's halfway between 3.00045 and 3.000.2.55. 1.05 kilohertz is right in the middle. If I can design a filter that will only pass everything 1.05 kilohertz either side of center, I'll have the filter I need. Now, no tuned circuit in the world can do that. Fortunately, we have other ways of filtering. Someone gladly, happily, wonderfully invented the crystal filter. As you know, crystals, I hope you know, crystals oscillate at a certain frequency. But there's something else they do. You can pass a signal through a crystal, and it will only pass a very narrow band of frequencies. This is such a filter. It's comprised of, I can't remember now exactly, I think there's 8 crystals in there. You can see 1, 2, and barely see the third one here. Yeah, there's 1, 2, 3, 4. Okay, there's 6 crystals in there. Plus there's some trimmer caps here, some toroid cores. It's a nice sophisticated filter network. This is a very tight filter. In fact, it's the exact filter we need. It's centered at the right frequency. It passes just what we want it to pass. So the crystal filter is our secret. Actually, the crystal filter is our secret weapon. Let's look at the complete transmitter, or almost complete transmitter. We have our speech amplifier, and it's only going to pass these frequencies. We have our carrier oscillator, which is 3,000 kilohertz or 3 megahertz. The balanced modulator, which you already know by now, will produce these 2 sidebands at this point. The crystal filter is not going to pass all of that. The crystal filter is only going to pass what it's designed to pass. We've now created a single sideband transmitter. Of course, the one problem is nobody wants to transmit at just 3 megahertz. So what we're going to do is we're going to add another oscillator here. Let's say this oscillator runs at 11 megahertz. We'll mix it. We'll get all 4 frequencies here. Remember mixing. We'll filter out the addition. 11 plus 3 is 14 megahertz. Now we're on 20 meters. We now have a 20 meter upper sideband signal. So step 1, we created 2 sidebands with no carrier. In step 2, we had to build a filter to select one sideband. We did this with a 3 megahertz carrier and a filter centered 1.5 kilohertz higher. This filter passes 2.1 kilohertz of bandwidth. That is 1.05 kilohertz either side of center. And there you have it. There's your filter. And yes, crystal filters can be that tight. This is a better look at the crystal filter's response. Now I've created some graphics to go with this that make it a little more understandable. Here is our upper sideband signal. If you look really closely, you look at these numbers here, we can go 1.05 kilohertz below or 1.05 kilohertz above. And we're still well within the bandwidth of the filter. As we go out farther, notice there's more and more attenuation. Like at this point, there's 20 dB of attenuation. What do you suppose would happen if our balanced modulator got a little unbalanced and some of the carrier started to leak through? Well, there's not too much to worry about there, because that's where the carrier is. And if you look really closely, the carrier is being attenuated at more than 20 dB. Now 20 dB means whatever energy comes through, whatever power level, is dropped by a factor of 100. So whatever power comes through in the carrier, only 1/100th of it makes it past the filter. Or to put it another way, whatever voltage level of carrier hits the filter, only 1/10 of that gets through. Now the next question is, what about the lower sideband? Where is it in all of this? Well, if you remember your frequencies from before, you know the lower sideband is down in this area. So let's take a look at it. There's your lower sideband. And at the best, it is attenuated 40 dB. That means it's attenuated twice as much as the carrier, and the carrier was just about obliterated by the filter. So there's no worry about the lower sideband sneaking through. That is not going to happen. In fact, most of the energy of the lower sideband is out in this area here. Now we are looking at close to 60 dB of attenuation. It's simply not going to get through. Let's talk about the crystal filter one more time before we go. As I've shown you, it's a real device. This one is about 55 years old. And it's the one, as I said, I'm using in my homebrew transmitter. The one thing I didn't tell you was that the frequency response or bandwidth isn't quite what I told you it was. The reality is my crystal filter doesn't really work at the frequency I told you. Here's a schematic of my homebrew transmitter. As you can see, the filter is a very simple device. It has an output, an input, and a ground. Notice the load resistor. This fights that thing about reactive loads bothering the filter. There's actually another resistor at this end. I just don't show it here. So as you can see, the filter is real, but what's not real is the frequency this one really operates on. This is the real frequency response of this filter. The reason I told you it was 3 megahertz, or specifically 3.0015 megahertz, is the math works out easier than if I had drug you through these awful numbers here. It just gets so confusing. So I moved the filter 394 kilohertz for the explanation. But other than that, everything I told you is accurate and the filter works as described. I assume that you have the following questions. How would you generate lower sideband? Well, you could just put another filter in, set up for the lower sideband frequencies, but nobody does that. I'll tell you how we do that in the next video. And how do you generate all those other frequencies? How do you really do that? It's not quite as simple as I explained, but it's not a whole lot more complicated either. Join me next time for DCL 303, Transmitting SSB. We'll address these two questions and try to tie up some loose ends. Thanks a bunch for watching, and I hope I did a really good job of hiding my allergies because I've been fighting them for 28 minutes.